So, Assalamu alaikum. We already solved these problems in class today. Okay. So go through them, solve them again. That's the only way you will improve. Okay. We solve this problem. We solve this problem. This problem, we solve it. And I told you how related it is to a spring. Okay. And yes. So we solve this problem. Well, quickly. We solve this problem. Okay. I told you about this problem. And this one. Now let me solve this problem because this is very important. So we have three identical particles placed on a straight line separated by a distance d, as shown in the figure below. How much work is done by an external agent to remove the particle at the center to a point far away? And you know that far away, u is equal to 0. Because I go at infinity, the gravitational potential energy is 0. So I give you the masses, m is equal to 2 kilograms, and distance, d is 2 meters. Of course, you know what is gravitational constant, right? 6.67 10 to the power minus 11 Newton multiplied by meter square divided by kilogram square. And you put the Newton in SI unit, it gives you this unit, meter cube divided by kilogram second square. Anyway, so here we have to use this. I need work apply. So we know that delta K plus delta UG is equal to work applied or work external. So here delta K is 0. Why? Because implicitly I'm telling you here that this structure made of free particle is at rest. And also when I take this gentleman and I put it at infinity, the structure is still at rest. So meaning what? Implicitly, you have the Earth implicit in the problem, okay? But that will just add a constant gravitational potential. And what we need is delta UG. The constant will go away. The change is what we need, the change in gravitational potential energy. So in reality, the initial velocity for this problem is 0. But when this one also go to infinity, well, the final velocity of the system is also 0. And when it goes to infinity, at infinity, the gravitational potential energy, of course, is 0, as said in the problem, but also the kinetic energy is 0. Because at infinity, we will stop anyway. You will start at some point. Okay? So the change in kinetic energy is 0. So here, what I need is the change in gravitational potential energy. And the work that I apply is equal to the change in gravitational potential energy. Now, that means work applied is UG final minus UG initial. What is UG final? Well, I remove this one. So I have only one pair. So UG final will be minus G mm, which is m squared, divided by the distance between them. And the distance between them is 2d. Minus, what is UG initial? UG initial is when this gentleman is here, okay? Because UG final, well, at infinity is 0. That's why I did not consider this in UG final. UG final, infinity is 0 for one particle. Now UG initial, well, I have this pair here, which is minus gm squared divided by 2d, but also I have this pair and this pair, okay? So I'll have minus 2 times gm squared, basically mass multiplied by mass divided by d. And this will give me what? Plus 2gm squared divided by d. And this is the work that I apply to do this operation. Okay, so this is what I did here. So, okay, clear all the drawings. Okay, Now to go to the next slide. So let me move this. Okay, and this is what I did. Okay, and I get it here. Now I put the the numbers and I get this. Now let me tell you something here. So it's a positive work. What does it mean? It means this was the initial state. This was the initial gravitational potential energy. Now I add the positive work to the system. So the work is going to an excited state. This is UG final. Of course, UG final minus UG initial is positive because work that I apply is positive. Okay. So what does it mean? You remember, I don't know if I said it, but this is out of scope of Physics 101. The ground state is what we call the lowest energy state. When I'm here, I want to remain here. Unless an external force bring a positive number and then I go to the excited state. So the external agent is adding this positive number of this positive energy to bring your system into just one mass here and one mass here. Okay. In other words, this is more stable. UG final is smaller than UG initial. The initial one was more stable because you have free particles attracting each other. When I remove the one in the middle, I put it at infinity, I go to this state, which is less stable. Now, if I did the inverse, I started with two particles, M and M here, and then I take one particle from infinity, same mass, and then I brought it in the middle, the work will be negative. That means I'm going from UG final here. Now my UG final will become my UG initial, then I'm going down here. And the work that I'm putting will be negative to go downward here. And that work is negative means I'm bringing the system to a lower energy state. Free particles attracting themselves is more stable than two particles attracting themselves. And the work is negative. And it, of course, it will be minus the work that I calculated. Okay, now let me go to this problem here, which is extremely important as well. So we have the potential energy, the gravitational potential energy of a rocket on the surface of the Earth, and I give you UG. Well, automatically, you know that this is at the surface of the Earth. So you note that UG is minus GMM divided by R, and R is the radius of the Earth here. And this is equal to what? Minus 624 10 to the power 10. So find the amount of work required to take the rocket to an altitude, remember altitude h, equal to half of the radius of the Earth. So h is half radius of the Earth. So r, as you know, is r plus h, radius of the Earth plus altitude. Altitude is the distance from the surface of the Earth. So here, of course, I'll have 3 halves of r. Now, what is the amount of work required? Well, you all know that work applied is delta K plus delta UG. Here, delta K is 0. Why? Here, delta K is 0. Okay, is it working? Okay, here delta K is 0 because I said that assume the rocket is at rest, both in final and initial position. Okay, please draw. Okay, so delta K is equal to 0. So work applied is just delta UG. So I will find UG final, meaning UG at this altitude, which is minus GMM divided by R, which is 3 halves of r minus UG initial. Minus UG initial, it will be minus, which is plus the mass of the rocket, mass of the planet, divided by radius of the Earth. Okay, here I'm saying that radius r is radius of the Earth. So, okay, this is what? This is minus U0. And this is minus 2/3 of U0. So I will find minus 2/3 of U0 plus U0. So this gives me what? Plus, yes, this, sorry. So this is what I called, yes, so this is what I called minus U0. So here you have minus U0, so plus here. So you have minus 1/3 of U0. And U0 is known. U0 is just this number here. Okay, so you get your answer. Okay. Now I am saying this because I want to go to the next problem, in which now, and you will see the difference. Why I want to solve this is because I want you to see this difference. Students who did this and who thought about the problem already saw it, but I want everybody to see this. Okay, it's not a big difference, by the way. It's just a little bit of work. You will realize it. So let me annotate and remove all my drawings. Clear all drawings. So now I have a satellite. Okay. In the previous problem, it was at rest at the beginning and at rest at the end. Now here, what do I have? I have the Earth, the solid sphere, mass m and radius r. Okay, so mass m, radius r. Now I have a satellite which is orbiting. I give you the mass of the satellite. It's 1,200. This is the mass of the satellite in a circular orbit. And the radius is 2r. Radius is 2r, meaning this. So the altitude here is r, of course. Okay, because you remember that radius is r plus h. So here radius is 2r, altitude is r. Good. Now, how much energy is needed to move this satellite from this orbit to another orbit of radius 3r? So now I have another orbit, the same satellite going into another orbit. Now the radius is 3r. Okay, so this distance here is 3r. So the satellite is moving now. So I need work applied will be delta K plus delta UG, because there is no friction force, of course. Okay, conservation of mechanical energy. But this is equal to what? This is equal to change in mechanical energy. Now this delta K is not zero anymore. Okay, that's what I want you to realize, because the satellite is moving and it has an orbital speed. And you remember what the orbital speed is gm divided by r. Okay, of course, v is square root of this. This is the orbital speed. Okay, okay. So the work applied is change in mechanical energy, not only just UG as in the previous cases. Now delta K is different from zero here. Okay, so this is work applied is change in mechanical energy, and it's a circular orbit. The mechanical energy is minus gmm divided by 2r. So that's it. So my work applied will be just UG final, which is minus gmm. And I know the mass of the satellite. I know the mass of the Earth. It's inside your formula sheet. Divided by 2 R final. R final now will be 3R. Minus UG initial. Minus mechanical energy initial. Mechanical energy is this. So you will have plus gmm divided by 2 times the initial radius, which was 2R. And that's it. Okay. So now this is what we did here. Okay. Minus gmm divided by 6r plus gmm divided by 4r. And this is what we did here. And you find gmm divided by 12r. and it's positive. The thing that I want to bring your attention is work applied here is change in mechanical energy. Okay. Whereas in the previous one, it was change in gravitational potential energy because delta K was 0. Here, I have a circular orbit. I have both kinetic energy and gravitational potential energy. And the work applied have to supply for the total mechanical energy. Okay. I want you to solve this problem as well. I will not. I hope I'm very clear. Okay. Well, you are very smart, so work and then you see it. So my battery is running low, but let's see this. Okay. So you know escape speed already. Escape speed, V escape, I already demonstrated in class, is square root of 2gm divided by radius of the planet. And this is coming from mechanical conservation of mechanical energy. Basically, at the surface of the planet, I have half mv squared, and gravitational potential energy, I have minus gmm divided by radius of the planet. At infinity, the mechanical energy is 0. At infinity. Okay, so this gives you a relationship between the escape speed and this, and you will find this. Now here I'm telling you that I'm firing a projectile here at the surface of the planet with half the escape speed. So basically I'm giving you the initial speed of the projectile. Now the projectile goes up. The question is, what is the maximum height? What is the highest altitude reach? So at highest altitude, of course, my kinetic energy will be 0. So mechanical energy initial is equal to mechanical energy final. What is mechanical energy initial? Is this half mv square, v square being this, minus gmm divided by r. And this is equal to mechanical energy final. Mechanical energy final, the kinetic energy will be 0. So it's purely gravitational potential energy. Okay, so it will be minus gmm divided by r. But r is equal to radius plus radius of the planet, which is the Earth, plus h. Now I know the radius of the Earth. I know everything here. The only unknown is this h, and you get it. Okay? Conservation of mechanical energy. I don't want to see conservation of mechanical energy and you are using mgh. No, for gravitation, conservation of mechanical energy now is different. Okay? I will not use gravitational potential energy as mgh. No, this is false. Okay, I will use gravitational potential energy as minus gmm divided by r. Okay, I want you to solve this. Solve this. Okay, solve this. This is very important, and we already solved it in class. But what I said in class was basically we find that free fall acceleration g is basically the gravitational acceleration minus the centripetal acceleration. Okay, and the centripetal acceleration is v squared over r, or r omega squared. Okay. R being the distance from the rotational axis. Okay. So when I'm at the pole, this r is 0. Basically, at the pole, at the north pole or south pole, g is equal to rg. There is no effect of the rotation, okay, on the free fall acceleration. Now, when I'm at the equator, now g will be equal to rg, and you remember rg, what it means is just gmm divided by r square minus r omega square, which is r omega is 2 pi divided by t, okay, square. So you see that the period or the rotation now will reduce the free fall acceleration, the measured acceleration. So go through this because this is a very nice problem. So you can rank these 4 situations. Here's the period is 16, period 24, period 48. And then I give you North Pole, North Pole, North Pole, and then equator, equator, equator. So now using these 2 information, you can rank them. Okay. I'm going very fast because I want you to do it by yourself and understand it, because the physics is here. I gave you the solution here. Okay, I want you to solve this, of course. I want you to solve this, of course, geostationary satellite. I want you to solve this, okay? This, I'll already talk about this many, many times. Okay, so let's stop here. Thank you very much. Inshallah. Assalamu alaikum. Bismillahir Rahmanir Rahim. Wassalatu wassalamu ala Rasulillah. So these are some recitation problem of chapter 13 that I want to add to what is already there on Blackboard. So before I go to the problems, let me just remind you a couple of things here that are extremely important. What is an energy of a satellite? So I have a satellite of mass m rotating or orbiting around a larger astronomical body of mass capital M. So I want to get the energy of this satellite, I mean mechanical energy. So I will do it for a circular orbit, C, and then I will generalize it to an ellipse, E. Let's start by a circular orbit. So as you know, if I have a circular orbit, the distance between the center of these two bodies is fixed, r is constant. Now, r being constant means that the speed is constant, okay? Because you remember, I have conservation of angular momentum for the planet or for the satellite. Basically, it's r, m, v. So if I fix r, I'm fixing v. Okay? So for a circular orbit, in reality, I have a uniform circular motion, okay? Where r is constant, of course. That means speed is constant, okay? And I have a uniform circular motion. Now let me apply Newton's second law on the satellite. I have net force, which is here equal to the gravitational force, is ma. But here, this a is a centripetal acceleration, AC, because the gravitational force is actually the centripetal force at the origin of this orbiting of my satellite or of my planet around the sun. If, of course, here I'm saying that I have a uniform circular motion. So gravitational force, which is Gmm divided by r square, is equal to the centripetal force, which is m. AC is v square over r. Okay. So this, if I simplify by m and I simplify by r here, I get the orbital speed. V square is just Gm divided by r. And this is what I call orbital speed. Okay. It's the speed at which my satellite in a circular orbit is orbiting around the bigger astronomical body. And you see, it's just depend on r. If r is fixed, v is fixed. And it does not depend on the mass of the satellite. Okay. So write this down. That means that the orbital speed is just square root of Gm divided by r, r being the radius of the circular orbit. And again, this is different from escape speed. Now, once I get the orbital speed, I can get the kinetic energy of the satellite. It's half m v square. So it will be half m multiplied by G m divided by r. So it's just Gm m divided by 2r. So this is a kinetic energy for what? For a circular orbit. It's just fixed by the radius. Okay. Good. Fixed radius means fixed speed, means fixed kinetic energy for my circular orbit. Now, what is my gravitational potential energy? This is always minus Gm divided by r, r being the distance between the two centers of masses. I add them and I get the mechanical energy, which is kinetic energy plus gravitational potential energy. So I'll have Gm divided by 2r minus Gm divided by r, and this gives me minus Gm capital M divided by 2r. And this is a mechanical energy. So if I have a circular orbit, the mechanical energy is conserved, and it's equal to minus Gm divided by 2r, okay? If you see this, this is just minus the kinetic energy. And this is true for a circular orbit, okay? And of course, for a circular orbit, the kinetic energy is just minus UG divided by 2. Okay? This is also true for a circular orbit. So for a circular orbit, I have this set of equations. Now let me generalize it for an elliptical orbit E. Okay? For an elliptical orbit, well, the mechanical energy, I will just replace R by the semi-major axis A. Okay? So the mechanical energy will not be minus gmm divided by 2r, it will be minus gmm divided by 2a. And this is constant. Okay? The mechanical energy is constant. Now, do you remember why the mechanical energy is constant? Because I don't have atmosphere. Okay? This planet here, or this satellite, roaming around in this elliptical orbit does not face air resistance. So overall, there is no friction. There is no air resistance. So mechanical energy is constant. Okay? The mechanical energy is constant for an elliptical orbit and is equal to minus gmm divided by 2a. Okay? Now, on the other hand, mechanical energy for an elliptical orbit is equal to kinetic energy plus gravitational potential energy. Now, of course, because it's an elliptical orbit, the kinetic energy and the gravitational potential energy are fluctuating because this distance here is changing. So UG, which is just minus gmm divided by R, this is true always, by the way. Okay, this R is changing, the UG is changing. UG is changing, of course, the kinetic energy is changing depending on R. And that's why I told you this point here is the fastest point and this point here is the slowest point and is the slowest point. Okay, so I will come back to this just in a second. I wanted to remind this because I did not have time really to stress it in class. I stress it, but not as much as I wanted. Now it's done. So this is what I talked about for a circular orbit. I already demonstrated this. Okay, for a circular orbit. This for a circular orbit, of course, I demonstrated it. And this is true for a circular orbit as well. I already talked about it. And if I plot them, this is what you have. K is minus E. So E here is minus K. And UG here is just, basically minus 2 times K. Okay. Good. So again, the kinetic energy is always positive. Of course, the potential energy and the total energy, mechanical energy is are negative. Okay. Good. Now here I already discussed this. When I have this, when R is increasing, the kinetic energy is decreasing. The orbital speed is decreasing. Okay. If I have a circular orbit, a larger radius means a smaller speed. Okay. Good. Now I can generalize this to an ellipse. And if I have an elliptical orbit, I have E is minus gmm divided by 2a. And this I already demonstrated it. Now the total kinetic energy just depends on the semi-major axis. Okay, it does not depend on the eccentricity. If you see here in this example here, all these, this is a perfect circle, by the way, and E is equal to 0.9 correspond to this elongated ellipse. Okay, but all of them have the same semi-major axis. Okay, A of all of them is constant and it's equal to the radius of this circle. So all of them have the same mechanical energy. Okay? This can be a nice checkpoint in coming exam. That was the reminder that I wanted to do for this part. Now let's go to the problem. The first problem is this. What do I have? A planet in another solar system. Its orbit a star, and I give you the mass of the star. At one point of its orbit, I gave you the distance between the two centers, between the planet and the star. And I give you the speed of what? Of the planet. The question is, what is a semi-major axis? Okay. So here I know that I have an elliptical orbit. Say my planet has an elliptical orbit, and this is a star. Of course, the star has a mass capital M, and the planet here has a mass small m. Okay. Okay. Good. And I give you the mass of capital M, but I did not give you the mass of small m. You will see that I don't need it. Okay. Now I give you this radius r, not the radius, basically the distance between the two centers. So r is equal to this. You put it in meters, of course. Okay. And also I give you the speed here. V in magnitude is 55 kilometers into the power of 3 meters per second. Okay. Now I'm asking you, what is a semi-major axis? This is not a very beautiful ellipse, but you get my point. Okay. So the semi-major axis is this. What is A? If you understand what I said before, I know that the mechanical energy of this elliptical orbit is the same everywhere, is constant everywhere. Okay. So mechanical energy here is equal to mechanical energy here is equal to mechanical energy everywhere is equal to minus G mass of the star, mass of the planet divided by 2A, A being the semi-major axis. Now this mechanical energy is equal to kinetic energy plus gravitational potential energy. Kinetic energy is half mv square, and gravitational potential energy is minus gmm divided by r. Okay, so I gave you v, I gave you r, I'm asking you a. Okay, of course here you see that this m will simplify with this m, will simplify with this m, so I'll end up with minus g m divided by 2a is half v square minus g capital M divided by r. So here I know everything. I know g, I know capital M, I know v, I know r. My only unknown is a. So get me my a, and you put it in SI units. Of course, it will give you this number. Now here, be careful. The speed, you should put it in meters per second. This r here, you should put it in meters, in SI unit. Why? Because this g is in SI unit, 6.67 10 to the power minus 11 SI unit. And you remember the SI units are Newton meter square divided by kilogram square, right? Okay. Good. So this is a very good question. Okay. And you should get this. Now I study about oscillation. I will tell you that the mechanical energy, E, of a spring block system is equal to kinetic energy plus spring potential energy. And this is a constant as well, half of K x max square. Okay. So this will be equal to half mv square. This is the kinetic energy of the block plus potential energy of the spring, half K x square. Okay. So I will be playing with this. I might give you V, I might give you X at a given point, and I will ask you what is XM. Okay. Or I will give you XM and K and M. I will ask you at this position X, what is the speed V? Or at this speed V, what is the position X? Okay. And this, let me remind you, but we will study this in detail. This is M, this is K, and of course, this is plus X max, and this is minus X max, and this is 0. Okay, and it's oscillating between these two maximum positions. So it's the same type of problem here. Now, well, this is easy. Okay. So I have conservation of angular momentum, okay, in my elliptical orbit. So angular momentum is conserved. So here, this is what we call the perihelion, the closest point to the sun. This is the aphelion. Okay. At the perihelion, I have the highest speed because I have the lowest radius. Sorry, the lowest distance Earth-Sun. At aphelion, I have the lowest speed because I have the largest distance Sun-Earth. Okay, but in both cases, I have angular momentum of Earth is the same. Okay, angular momentum is just here. You see here you have 90 degrees. So angular momentum will be just mRV. Now it's true for aphelion, but also it's true for perihelion. Okay. So I gave you everything, so you can get what is the V at perihelion, and then you can calculate the kinetic energy at aphelion. Okay, you can get a VA at aphelion, and then you can get what is the kinetic energy at aphelion. Okay, and again, I'm rotating counterclockwise. I'm rotating in this direction. Okay, good. So this is the same type of problem. Okay, I told you that the law of areas, okay, is coming from conservation of angular momentum. Okay, so the law of areas is basically the derivative of the area with respect to time is just the angular momentum of the planet divided by 2 times the mass of the planet. If angular momentum is conserved, the area swept per unit time is conserved, is a constant. And here I gave you everything, and I'm just asking you what is the mass of the planet. Okay, I gave you the angular momentum, I gave you this, okay, area per unit time. I'm just asking you about m, and you can get it easily. Okay. Now, let me say something here. I used to give a nice example to my students. I told them that this sun is the exam and this planet is a student. Okay. And it's rotating counterclockwise. Okay. Now, when the student is coming close to the exam, he's going faster. And then once he passed the exam, now he becomes lazy and lazy and lazy and lazy. And then when he reaches here, this is the point where he is slowest. And then he sees the exam again, he starts going faster again, you see? So in this part, the speed is accelerating. In this part, it's decelerating, with these 2 points being the maximum speed and the minimum speed. Maximum speed is perihelion, minimum speed is aphelion. But between here, it will be, of course, accelerating. Here, it will be decelerating. Okay? This is a student, this is the exam. Okay? Good. Now, let's go to this problem here. At which altitude above the Earth's surface should I have an acceleration due to gravity of 1.7 meter per second square? You know that the gravitational force is g, mass of the object, mass of the Earth, divided by r squared. R being the distance Earth object, center of the Earth and the center of the object. Now, if I use Newton's second law, this is just m multiplied by ag. So that means my ag here is just equal to this, okay? This part. Basically, gravitational acceleration is just g mass of the Earth divided by r squared. Okay, good. Now here I gave you ag. Ag is 1.7 meters per second square, and I know g. I know the mass of the Earth. You check your formula sheet. Mass of the Earth is just 5.98, 10 to the power 24 kilogram. So you plug it here, and now your r, as I told you in class, r is just radius of the Earth plus altitude h, okay, square. So I know everything here. My only unknown is this h. Okay? And you do it, and then you will get your answer. Of course, put everything in SI units, okay? Meter per second square, this is in SI unit, you know the mass, it's in kilogram, you know r, radius of the Earth, you know radius of the Earth, right? 6,370 kilometers, you put it in meters, of course, and the only unknown is your h, okay? Again, your altitude, if this is the Earth, it has a radius r, e, and a mass me. The altitude here is the distance from the surface of the Earth. This is h. So the total r is equal to radius of the Earth plus h. Okay, good. That's very simple. Now here also you can solve it easily. Okay, I give you Jupiter. Okay, and I ask you what is the gravitational acceleration at the surface of Jupiter. So you know, okay, at the surface of Earth, Ag at the surface of Earth is radius of Earth. This is basically g, which is 9.8. And I told you how to get it. It's g, mass of the Earth, divided by radius of the Earth square. This is roughly 9.8. Okay. Now I want to calculate it at Jupiter. Okay. So I call it Ag Jupiter or G Jupiter. Of course, it will be g, mass of Jupiter, divided by radius of Jupiter square. Okay. So now I will have it. Okay. I know G, mass of Jupiter, you know it, 318 times mass of Earth. Okay. Radius of Jupiter is 11.2 times radius Earth square. Okay. So that means I will have G, mass of Earth, divided by radius of Earth, multiplied by 318, divided by 11.2 square. And this is G basically. Okay. This is 9.8 multiplied by 318 divided by 11.2 square. If you do this, of course, you will get your answer. You know this very well from your lab. Okay. In the simulation, you know that the G of Jupiter is 24.8 meter per second square. Okay. Yes, 9.8 multiplied by 318 divided by 11.2 square. Okay, good. Is it clear? Okay, I want this to be very clear. Okay, so here, read carefully. So I wanted to solve this because a good student came to me. I want me to solve them. And I agree because I solve other problems. But these problems, I have them, but let me just redo a video for them just for you. Disability, of course. Okay. Okay, and I want you to get a good grade in the final exam. So I have a satellite which is orbiting around a uniform spherical planet. This is very important. Close to its surface with a period of 6 hours. Find the average mass density of the planet in kilogram per meter cube. I don't need to draw, but drawing is excellent. Okay, we are in physics. So this is my planet. It's a sphere. It has a radius r and a mass m. Now I have a satellite which is orbiting close to the surface. So the satellite is orbiting around the surface, just close. Okay. This is supposed to be a circle. Okay. My circles looks bad, but you understand what I mean. Okay. So the altitude here, h, is very small. So the radius of the orbital, the uniform, because it's orbiting in a uniform way. So basically it's orbiting in a circular orbit. Okay. So you know that this is third law of Kepler. T square is just 4 pi square divided by gm r cube. Okay. So this is the third law of Kepler, right? Now I have the third law of Kepler. I forgot something here. Okay, so this is the third law of Kepler. Now I gave you T. I did not really give you R, but you can get it. Here, R is R plus H, but H is very small compared to the radius. That's why I said close to its surface. So that means R, small r, is roughly the radius of the planet. Okay. So I will write it down here. So T square is just 4 pi square divided by gm multiplied by the radius of the planet cube. Okay. Now, of course, I gave you T, you put it in seconds. Okay. I gave you T is 6 hours, you put it in seconds. Right. Now, the question is, I want the density. Okay, easy. Now, the density, rho, is mass of the planet divided by volume of the planet. It's equal to what? Mass of the planet divided by 4 pi divided by 3 r cubed. Okay, the volume of the planet is spherical and it's uniform. Okay. So you see here what? You see that, well, actually in the period here, if I say T square, which is 4 pi square divided by gm, and I divide by r cube. So this, I kind of have it here. Okay, m divided by r cube is just 3 divided by 4 pi multiplied by density. So I just plug it here. I'll get T square is just 4 pi square divided by g. Now here I will have 3. Okay, so yes, here there is a mistake, of course, right? Okay, so this is 4 pi divided by 3. Okay, Okay. So here I will have what? 4 pi divided by 3 multiplied by rho. Okay. And you see that this 4 in this 4 will go away, this pi and this pi will go away, and you will end up with t squared is just basically 3 divided by g rho. Okay. So this is what I have. And then I have, of course, here a pi. Okay. So I end up with t squared is just 3 pi divided by g rho. That means rho is equal to 3 pi divided by gt squared. And you do it properly. You put g is in SI unit. Of course, the period you change it in second, and you will get 303 kilogram meter cube. Okay. Straightforward, very interesting. Now, okay, I can ask this question different ways. Okay, this is another way. Please have a look at it. Okay. This is another way to ask the same question. Now, for the rest of the time, I want to solve this problem and this problem. Now here, what do I have? You read the question carefully, okay? This is an A+ question as well. A spherical planet has a uniformly distributed mass, m, and radius r. The gravitational force of the planet on a mass m located at an altitude 2r above the surface of the planet is F is equal to 4g, where g is the Earth free fall acceleration. Okay, let me just draw that. So this is my uniform planet. It's a uniform spherical sphere. It has a radius r and a mass m. Okay, now I have an object here. It has a mass m, and the altitude, the distance from the surface, is 2r. Okay, that means the total radius here, r, basically the radius of the orbit, is r plus h. Okay, is radius plus h. Okay, so it will be r plus 2r, because this altitude here is h, right? So this will give you 3r. Okay, and I'm telling you the gravitational force here. What is a gravitational force here? Well, as you know, Fg is g, mass of the object, mass of the big astronomical body, divided by r squared, r being this distance here. Okay, good. So, and this, I told you already, this is equal to 4g, according to the 4mg, sorry, according to the problem. Okay. This is equal to 4mg. Now, that will give us what? Now, let me change the radius by its value. So this will give me g m divided by 3r squared, and this is equal to 4mg. Okay, so I have my first equation. Okay, and I will see what it will give me. Okay, now I don't need to change the values, because you see here I don't want the values. I want it in terms of mg, so I'll keep it as it is. Now, next, what will be the force on the mass m if it's located at a distance r divided by 4 below the surface? So here you have to use the second shell theorem. This is my planet, okay? And now the object of mass m is here, okay? And this is r divided by 4. So the center of the planet is here. So this distance here is what? 3r divided by 4. So 3r divided by 4 plus r divided by 4, that will give you the radius. Okay. Now the question is, what is the gravitational force if my object is here, m? Well, I have to build the inner volume, okay? Because the shell theorem is telling you that only this inner mass, this mass inside my inner spherical shell, will exert a gravitational force on this object, which is here. This mass here will not exert any gravitational force, because this is a shell theorem. So let me calculate that gravitational force. The gravitational force will be G, mass of the object multiplied by mass inside. Mass inside is a mass of this inner spherical object, uniform spherical object, divided by r square. But r square here will be 3/4 of r. So it will be 3 divided by 4r, and I take the square. Okay, so the gravitational force that I want will depend on the mass inside. Now, how will I get the mass inside? You will use the fact that the density is uniform. Density rho is constant, so it will be equal to mass, total mass divided by total volume, 4 pi divided by 3r cubed. But it's also equal to mass inside divided by 4 pi divided by 3 radius inside, and radius inside is 3 divided by 4r cubed. Okay, so I will use this. So 4 divided by 3, 4 pi divided by 3 will go away, and then I will have that mass inside. And we did this in class already, guys. Okay, if you remember correctly, will be total mass. Now I will have what? Of course, the r cube will go away. Okay, so I will have total mass. Now I will multiply it by 3 divided by 4 cube. Okay, this is mass inside. Now I will bring it and plug it here. Now gravitational force will be what? Gm. Now mass inside, I will replace it by m, and here I will have 3 divided by 4 cube. Okay, and here I will divide it by the radius, which is 3 divided by 4 square multiplied by r square. Okay, good. But remember something. Okay, let's do it properly. So what I will have here, of course, here I will have this. Okay, this and this will go away. So I will have what? 3 divided by 4 GMM divided by r square. Okay, good. Now here, let me do something here. Okay, let me multiply here by 3 square. And then here, I divide by 3 square. Okay, so I will have 27 divided by 4 GMM divided by 3 r square. But remember this is equal to what? This is equal to 4g. So I will have 27 divided by 4 multiplied by 4 mg. The 4 goes away, and I will have 27 mg, which is the solution here. Okay, and this is an A+ problem, of course. Okay, so please solve it and be comfortable with it, because I'm using different things. Altitude was the first difficulty, and then I put it outside, and you have to get this. And then I put the particle and I put it inside. You have to use a shell theorem, meaning you have to find mass inside using the constant density. And then you plug it in your gravitational force here. And then you compare with this, and you will see that it will be 27 mg. Is it clear? Okay, good. Now I will finish by this problem here. I have a satellite, and I give you the mass of the satellite. It orbits, it's a circular orbit, the Earth. Okay, and I give you the radius of the orbit, 2r, where r is the radius of the Earth. How much energy is needed to move the satellite from this orbit to another orbit of radius 3r? So here, all what I need to apply is work applied is delta K plus delta UG, meaning work applied is delta mechanical energy. Okay. Now, what is mechanical energy? Of course, it will be delta mechanical energy final minus mechanical energy initial. Okay. And you know that for a circular orbit, mechanical energy is just minus GMM divided by 2R, if you remember correctly. Okay, so this is what I did here. Okay, so my R initial is what? 2R, and my R final is 3R. So work applied, which is mechanical energy final minus mechanical energy initial. Okay, so it will be minus GMM divided by 2R final, which is 6R. Okay, 6R. Be careful, my 6 looks like a G, but it's a 6. Okay, plus GMM divided by 2R initial, and 2R initial is equal to 4R. Okay, and then you calculate it, it will give you this. Okay, let me stop here. The rest, I want you to solve it by yourself. Okay, what is a geostationary satellite? There is a lot of discussion here. It's just good for you to know it. I have this binary planet, this binary star system. Our star is not binary. Okay, our sun is one system. Okay, so solve it. The solution is given, and I want you to solve this, of course, and you solve everything. Okay, and you understand them. That's more important. So thank you very much, and salam alaikum.